In the previous video, I talked about scientific notation, why numbers are important. Now to the dilution problems. First I wanted to just back up a little bit. The general purpose of bacterial testing is to really primarily look for safety concerns. So thousands of these sorts of tests are being run every week around the country. I've been involved in sampling rivers and streams, for instance, and we did these types of tests to determine the quality of the water. They're being done at water treatment plants, and they're being done in food testing and other applications. The goal is to look at the safety of these materials and consider whether people are at risk from being exposed. Most of the actual pathogens that we're looking for there are gastrointestinal bugs that cause diarrhea, and we're disgusted by those sorts of things because in the past our ancestors were safer if they stayed away from them. These are dangerous materials because they can contain pathogenic viruses and bacteria. But when we test, what we're looking for are coliform bacteria, and these are just super abundant in the large intestine and in feces of vertebrates. Most of them are not pathogenic. They're friendly bacteria. They actually help improve our health by being in our large intestines. But they are indicators. They're a red flag. They're telling us that feces is in that sample. And if so, other dangerous bacteria and viruses might also be present. The virus that causes hepatitis A, the bacteria that cause diarrhea in the case of Shigella, they cause dysentery. In the case of cholera, those are Vibrio bacteria that cause deadly cholera outbreaks. It's hard to test for those pathogens directly because they are often kind of rare, and there's so many different possible kinds. You don't know what might be circulating in the community, and so you don't know what to look for. Instead, we look for something that is always present in high abundance in feces, and those are the coliforms. To a more specific question, why do we do this dilution math? We can't see and count individual bacteria, so we take liquid and make a spread plate, and then we grow them out and we look for colonies. The bacteria are so concentrated that if we put pure sample on a plate, we would get thousands of colonies, too many to count. So we dilute the sample to create different strengths of solutions, and then we make a series of spread plates, and the goal is to get at least one plate with a countable number of colonies. 30 to 100 is ideal, and then we can calculate the concentration of bacteria that were in that original sample. The first step in understanding dilution math is the calculation of dilution itself, and that's whatever the volume of the sample was divided by the final volume after you dilute the sample. So for the first example, and you can try the others yourself, you transfer 1 ml of bacteria into 99 ml of sterile saline. Sometimes it'll just be water. That's the sterile fluid that you use to dilute the sample. The dilution in this case would be 1, that was the volume of the sample, divided by 99 plus 1, which works out to 100. That's the final volume after you mix those two things together. And as you should remember from the scientific notation work that you did, that's 10 to the negative 2, and can also be expressed as 0.01. Now, when you start with a sample, you don't know how many bacteria are in it. That's the whole point. We're trying to find that out. And so we don't know how much we have to water it down to get a countable number of colonies on the plate. And the strategy then is to make several plates with different dilutions in the hope of getting one that works. And this is what leads to serial dilution. So for the first example, you might transfer 1 ml into 9 ml, and then you might take some of that and transfer 1 ml of that into 99 ml of saline or water. What would the final dilution be in that case? Well, the way to figure it out is to take the dilution of each step and multiply them together. So we have 1 divided by 9 plus 1, which is 10 for the first step. And then we have 1 of that divided by 1 plus 99, which is 100 for the second step. And the product of those two is 1 divided by 1,000 now, 10 times 100. And if you remember your dilution or your scientific notation, 1 over 1,000 is 0.001, or 10 to the negative 3. Here's one for you to try, and then we scroll down. Pipetting is time and labor intensive. You have to throw away a lot of pipettes, and to save on this cost, you can sort of get an extra dilution by doing a shortcut. You take a solution that you've prepared and you make 2 different plates with it. One of them has 1 full ml of that solution. You make the spread plate that way. But the other one has 1/10 of that amount, 1/10 of a ml. The second plate is diluted more than the first one because you just used less of the solution. And you should get about 1/10 as many colonies on that plate compared to the one where you used a full ml. I think that the term for this is plate dilution. So here's an example of that. You transfer 1 ml into 99 ml of sterile saline, and then you use 1/10 of a ml of that to make a plate. What would the actual dilution of that plate be? It would be 1 divided by 99 plus 1, which is 1,000. All right. 1 over 1,000. Sorry, it's 100. 1 over 100 times 0.1. And 0.1 is 1 over 10, right? It's 1/10. You could just multiply by 0.1 on your calculator, but sometimes it's helpful to be able to write out fractions to make it easier to do this math in your head. So the product of those two fractions is 1 over 1,000. And that, as you remember, is 10 to the minus 3. Now you have one to try on your own. Calculating the actual bacterial concentration is the whole purpose of this exercise. And the way you do it is you take the plate colony count, number of colonies on the plate, times what's called the dilution factor. What is that? Well, it's 1 divided by the dilution. And if your dilution is already expressed as a fraction with 1 on top, say 1 over 1,000, then the dilution factor is just the same fraction upside down, 1,000 over 1. So that's a simple way to get the dilution factor. Flip the fraction upside down. Here's an example. You count 42 colonies on a plate with a dilution of 10 to the negative fifth. What was the original concentration of bacteria in the sample? It's going to be 42, the number of colonies, times, how much? Well, I'm given the scientific notation 10 to the minus 5. How many, what's that in terms of a fraction? Well, it's 1 divided by 10 to the fifth. And in standard notation, that number would be 1 followed by 5 zeros. 1, 2, 3, 4, 5. Helps to put commas in to see what that number is. It's 100,000. That's the dilution, but now we have to flip that. I just did this as a kind of a shortcut so you could see how I'm calculating it. You're not actually going to multiply by 1 over 100,000. You're going to multiply by 100,000. All right, you're going to flip that fraction over. Equals. And then you can use your calculator, or you can do it any number of ways. And the answer is 4,200,000 colonies or cells per, I guess, milliliter in this case. Now, there's room for error in that. You need a calculator. It's a little bit awkward. There's a shortcut that you can do using scientific notation, which is it's 42 shift times 10 to the positive fifth. So all you need to do is reverse the sign on the exponent there. And this isn't quite expressed in scientific notation. Remember, the coefficient has to be between 0 and 10. So if I change that to 4.2, essentially I have to increase this value because I decreased this one, right? So I went from 42 to 4.2. I divided that by 10. To keep the value of this entire expression the same, I'd have to multiply that by 10. And so that'll be 10 to the 6th power. If you remember from before, the waypoints for these exponents are multiples of 3. So 10 to the 3rd was 1,000, 10 to the 6th was 1,000,000. You can quickly look at this and see, oh, yeah, that's the same number as that. And this is a more compact way of expressing that number with less room for errors in how you write it out and that kind of thing. Here's one for you to try on your own, and another one to practice with. This last question kind of challenges you to do the whole procedure from start to finish. And I will provide you with answers for those. I'm not going to